In this video, we'll be talking about the ratio test. Now, we could also go through the proof of the ratio test, but we're going to go ahead and bypass that. Just keep in mind that the ratio test does have some comparisons to that of the the limit of partial sums in its proof. But overall, we're just going to go ahead and utilize the ratio test. So, the ratio test specifically states that if I have a series a sub k, and it is an infinite series, again, I'm going to avoid the bounds because we're applying that it goes from 1 to infinity, such that the terms are positive. Now, what's nice about this is that in almost all cases, the terms that we're going to play with, the a sub k's, will almost always be positive. We have different rules for if the terms are negative and when we're going to use those. But in almost all cases of the ratio test, when you're asked to use the ratio test, or when you think to use the ratio test, the terms being positive already present themselves kind of logically. And then we're going to go ahead and let this r, we're going to call this r for the ratio, equal to the limit as k goes to infinity of a sub k plus 1 over a sub k. So what we're going to do then is we're really going to go ahead and look at this detail right here. If I have a series of a sub k such that all the terms are positive, I'm going to evaluate this limit. There are 3 possible occurrences with that limit. Now, these 3 possible occurrences kind of condense down to the concept of 2 possible conclusions. And the first one really is if 0 is less than or equal to r, which is less than 1, if I conclude that this thing right here, now let's talk about the ratio test in terms of the hand-wavy understanding concept as opposed to a proof. This is the kth plus 1 term of the sequence, and this is the kth term of the sequence. If I take the limit as k goes to infinity of this ratio, of the comparison of the next term divided by the previous term, and that ratio is getting to a value somewhere between 0 and 1, it means that these values here overall are fractions. They're fractions less than 1, which means that this top term is going to be a value smaller than this bottom term. And if the ratio r, the limit as k goes to infinity, if these values approach something that is a fractional value or something less than 1, then arguably this thing is getting smaller than this one indefinitely. And that's the idea that we want to use to prove the concept of the ratio test, is that if I can identify that the next term in the sequence is getting smaller and smaller and smaller, then it's kind of like I'm showing the proof of that the terms will eventually cascade to 0. So if this is true, the leading concept is the series a sub k will converge. That is the end result. If I can prove that this limit of a sub k plus 1 over a sub k is equal to 0 to 1, not including 1, then that thing is convergent. Number 2, if I can conclude that r is greater than 1. So if the terms on top happen to be larger than the terms on the bottom, then we're saying that the terms are slowly getting larger and larger and larger as we go, and that should imply then that the series a sub k will diverge. The third case, and again, it's really not really a case at all. It really just says we don't know anything, and that's the piece where I've left out. So what if r is equal to 1? Then the test is inconclusive. Very much like that of your divergence test. If we get the limit equals to 0 for a divergence test, then we don't know any new information. We can't say that it's convergent or divergent in any way. Just like that, we have these 3 statements. If I get a value between 0 and 1, I have convergence. If I get a value larger than 1, I get divergent. But if I equal to 1, then the method that we're attempting to use doesn't work, and we have to try a new method. So let's talk about a couple of examples for this. The first example we're going to go ahead and work with is the summation of k equals 1 to infinity of 10 to the power of k divided by k factorial. So just like with integrals, we had a certain method to attempt when we solve certain things. The ratio test is most effectively used in almost all circumstances where there is a factorial in the sequential term. And the reason for this is because we don't know how to take the limit of a factorial. Taking a limit of a factorial, it's a difficult concept to wrap our minds around, because this factorial is really k times k minus 1 times k minus 2 and so on and so forth until we get down to 3, 2, and 1. The issue with this k factorial is the fact that if k is changing, then it's going to be 10 times 9 times 8 times 7, and then in the next term, as it continues moving further, it's going to be 11 times 10 times 9, and then the next term it's going to be 12 times 11 times 7. And so this value is just going to keep getting larger and larger. like it would logically, but we don't know how it's going to compare mathematically or algebraically to the top stuff. So this is where the ratio test comes out really nicely. So recall the ratio test. All the terms are positive, which in most cases they are. R is going to be equal to the limit as k goes to infinity of a sub k plus 1. Okay, so I need to figure out this right here, I have to make note, is a sub k. So my denominator, my limit, my r value, limit of k goes to infinity, my a sub k is in the denominator, my a sub k plus 1 is in the numerator. So my a sub k is this thing. So in the denominator, I'm going to have this. I'm going to draw it with a slanted division symbol so I can tell the difference between the top and bottom of this overall thing. Now the top is going to be where I take my a sub k and I replace it with a k plus 1 in all of those terms. So this k is now k plus 1, this k is now k plus 1. So I have 10 to the power of k plus 1 divided by k plus 1 parentheses factorial. And again, like I had said, doing this ratio test in terms, or taking any limit with a factorial is going to get really complicated really quickly. But what's nice about this entire step is that it's this fraction divided by this fraction, but I can use keep, flip, change. So this becomes 10 to the power of k plus 1 all over top of k plus 1 factorial multiplied by, keep the top, flip the bottom, so this becomes k factorial over 10 to the power of k. And if we just do some basic algebraic rules on this, 10 to the power of k plus 1 is really, let me change this or rewrite that limit, this is 10 to the power of k times 10. And this k plus 1 factorial, let me go ahead and write that out for a second. K plus 1 factorial is really equal to k plus 1 times k minus 1 times k minus 2 times dot, 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 dot until we get them to 3, then 2, then 1. And you'll notice in this k plus 1 factorial that this whole thing right here is nothing more than just k factorial. So that means that this k plus 1 factorial is really k plus 1 times k factorial. And that's how I'm going to write that in most cases. If it was k plus 2, then it would be k plus 2 times k plus 1 times k minus 1, and so on and so forth. And therefore, I'd have k plus 1 and k plus 2 times k factorial. This is still times k factorial over 10 to the power of k. And you'll notice, oh so conveniently, that I have a 10 to the k on top and on bottom. I have k factorial on top and on bottom. And I'm left with that this limit as k goes to infinity of 10 over k plus 1, which goes to 0. So therefore, and again those three dots mean therefore, by the ratio test with r equals to 1, the series 10 to the power of k over k factorial is convergent. And again, it's convergent not because I ended up with equaling to a number, but it's convergent because that number happens to be between 0 and 1. Again, my r value, the limit of the ratio, has to be between 0 and 1 or equal to 0 for the overall series to be convergent. Let's go ahead and do one more example on this. This particular next example actually has to deal very closely with some other details that we've worked with in the past. So we're going to go ahead and look at this one. So in this example, again, the rules still apply. The minute I start seeing ugly powers, and again, that's the other idea, is that if I see some kind of powers in here, so 10 to the power of k, we can start working with the ratio test. But now that I have a k to the power of a k, this is going to get kind of heavy real fast. But the fact that there's a factorial in here leads me to consider the ratio test as an option. So I'm going to go ahead and do ratio test, which is r equals to the limit as k goes to infinity of, and I'm going to do this very carefully, but I'm going to do it relatively smooth. So I'm going to take this thing right here. This term is supposed to be my a sub k, so that is the thing that's supposed to be on the denominator. Again, the ratio test specifically shows that we're supposed to have a sub k plus 1 on top and a sub k in the denominator. So this thing is going to be in the denominator. I'm going to go ahead and avoid writing that for just yet, but what I'm going to do is I'm going to go ahead and write the a sub k plus 1 as the numerator as a base piece. So all my k's are now k plus 1. So there's k plus 1, there's k plus 1, that's k to the power of k, so now it's k plus 1 to the power of k plus 1, divided by k plus 1 in parentheses factorial. So that right there is the top stuff. This is technically supposed to be divided by, I'm going to draw this nice big giant fraction bar, a sub k, which is k to the power of k divided by k factorial. Now again, I will probably avoid writing this in any other type of view, and I'll jump straight to the limit as k goes to infinity of k plus 1 to the power of k plus 1 divided by k plus 1 factorial times k factorial over k to the k. In doing so, this provides me with a way that I can very easily deal with the factorials. Again, noticing that k plus 1 factorial is really just k plus 1 times k factorial. So I can cancel out this k factorial here with this k factorial here, leaving me with this k plus 1 strictly on the bottom. Then it's going to be a little bit tricky to work with this and this. But what we're going to do here is we're going to go ahead and ever so carefully pull apart the top piece here. And now keep in mind, if this was with this being k plus 1 to the power of something, I can't distribute powers over addition or subtraction. So don't think that this k plus 1 can be distributed to this one and allow us to work with it that way. That can't happen. But what I can do is I can do the same thing I did with the last problem and change this k plus 1 to the power of k plus 1 into k plus 1 to the power of k times a k plus 1. Again, that's the part that's to the power of 1. This is still divided by k plus 1 from the factorial stuff, and this is still multiplied by 1 over k to the power of k. Well, hopefully those things will help us cancel some stuff out. And sure enough, this will cancel out with this, and I'm left with the limit as k goes to infinity of k plus 1 to the power of k divided by k to the power of k. But if you recall, the fact that there's an exponent on this stuff and the exponent is the same, powers can be distributed over multiplication or division. So I can technically undistribute them, making this k plus 1 all over k to the power of k. Now, at this moment, while we're trying to look at this thing right here, the idea is that this is the limit as k goes to infinity of k over k plus 1 over k, all to the power of k. And we'd hope to God that we can go ahead and conclude that this is 1 plus 1 over k to the power of k. And as we conclude this concept that this should be, well, this inside stuff goes to 1 and the top stuff goes to infinity, so this thing goes to 1, question mark, and that's not true. You have to recall that anything to the power of infinity such that it's 1 or 0, you don't necessarily know what it's converging to. This is one of those indeterminate forms, and this is one of the real clear, viable reasons as to why. If we were to go ahead and use the skills of letting y equal to this function 1 plus 1 over k to the power of k, and we take the natural log of both sides, natural log of that equals to the natural log of 1 plus 1 over k, such that the k comes down in front as a multiplication, we can then take this setup here and attempt to evaluate this limit. In doing so, and again, this has been done in the past, this overall thing here ends up converting to just be 1. So this doesn't equal to 1. This limit here will eventually equal to 1 using the appropriate L'Hopital's rule steps. I get the natural log of y equals to 1, and therefore y, if I'm taking the limit of it, is equal to, again, this is equal to 1 using the limit, so I should probably attach that in there, that this is equal to e to the power of 1, which is really just e. And again, we've done that limit before in lecture in class, but that right there is the value that, let's scroll all the way back up, that r happens to be. So if we look back one more time at our ratio test, we did a lot of work to get there. We set up this thing right here, and we evaluated, and we got a value of e. E correlates to being something larger than 1, so this overall series will diverge. So, back up here, by the ratio test, the series, k to the power of k over k factorial, is divergent.